Hello everyone, my name is Pranagopal Karande. I am from batch B4 studying ENTC, and today I will be presenting my work on brief overview of Verilog and its code in this course Digital System Design. So let's begin. So now I will share my PPT over here. So Verilog is basically a hardware description language that is used for designing and modeling digital circuits. It's a powerful tool for creating complex systems from simple logic gates to microprocessor. So before that, I also studied VHDL. So in VHDL and Verilog, while studying both of them, I found there are somewhat similarities and somewhat difference. The difference that I found is that between syntax and their readability, and there are some data types that are different. For example, in if we say VHDL, that is standard std logic underscore bit or int, and then if we see in like Verilog, then there is wire and there is reg and there is integer. So that is the difference between Verilog and VHDL. So let's now see the history behind Verilog. So Verilog was developed by Phil Murby at Gateway Design Automation in 1984, followed by that same year in after 1 year in 1985 its first version Verilog XL was released, and in 1995 it became an IEEE standard. In 1999 and 2005, Verilog 2000 was introduced and System Verilog was launched. And now Verilog is also widely adopted and used in semiconductor and EDA industries nowadays, and it is very popular. Verilog basics and syntax and structure. Now, if we say in VHDL, we have seen entity where we declare ports, and architecture. There is one declarative part where we declare signals, and below begin we write their main body of the code. So same like that, there are two sections, that is declarative and procedural section. In declarative, we can see that it includes module. That is a new stuff that we'll learn in Verilog basics. And then there are ports and variable. Any procedural, there are hardware operate, that is include data flow, timing, and logic operations. So in this is the definition of module. So in the right you can see an image. So basically this is an syntax of overall, we can say Verilog. So it begins from the keyword module, and then we give a module name, and in the port list we pass away the inputs and outputs, and below that, that is the interface, where it will be showing that the A is an input or B is an input or C is an input, and then sum or a carry is an output. That is a what I have said is a full adder that we will be doing ahead. And then we can do add-ons, that is include directives, the main body where we will write the code, and then we will end this module by the keyword end module. So combinational logic design in Verilog. So a combinational logic circuit produce output that depends on the current input value. So inputs are directly connected to the circuit outputs, and then logic gates are also important because we type those codes on basis of gates, that how many logic gates are present and their combination that are possible. So now let's start our journey, that is developing a full adder in this Verilog. So I have written that in steps. So first is define inputs and outputs. So I will show you ahead the for truth table also, and the circuit diagram also. So yes, so define inputs and outputs. Second is sum and carry out calculations. So I have declared A, B, and C in, and sum and C out. And then we will use some gates, and in the end, our code will be ready and we can get a full adder. So this is the truth table and the circuit for full adder. And here is our code for the Verilog for a full adder. So here I have declared inputs A, B, C in, output is sum, output is actually it's C out here, but I have shifted to carry. And I will show you the code in Xilinx now. So this is the whole code that I have typed. So now let's see what is actually happened. So as you can see, module keyword vary underscore full is the module name, and inside that all these are nothing but the port, that is A, B, C in our inputs, sum and carry are the outputs. Now what is this wire? We can see wire. and S1, CL1 or C2. So now let's go back to our diagram. We can see full adder circuits and truth table. Now if we observe this first XOR, I am rotating the cursor over here, then this output is directly to the input of the second XOR. So now for the code, if we have to write, then we have to write in this manner. That is S1. That is S1 is the output and A and B are the input. For the XOR, that is XOR 1. And for XOR second, we can see the S1 is acting as an input and then Cin as sum is produced. I will repeat. So over here, this is an input to this XOR gate. So this is nothing but wires. So there are different totally of three wires. First is over here, second is over here, and third is over here. So that's how we will write five totally codes. That is 2 XOR 2 and 1 OR. So now let's check the syntax over here. So it's, check syntax was completed successfully. We'll view the RTL schematic. So this is our full adder. We can see over here. So this was the Verilog code. So now what about the test bench? So test bench is also similar, or we can say it was similar to VHDL when I was typing the code. So for let's now create a separate file, that is new source. We'll create a new file over here, that is, we can say anything like very underscore full, and then Verilog text feature. As in VHDL we used to choose VHDL text bench, so in Verilog VHDL text feature. So this is where we will write our behavioral or test bench. So almost till now we can say that it was like similar only to VHDL, but there are some syntax and there are some different types of data types that we will be using. So yes, here it has been declared already. So to save time, I will just use this code over here. So here I have done nothing but I have just given the input values, that is A is 0, B is 0 and Cn is 0, just as shown in this about truth table. A0, B0, C0 and then AB0 and Cn1. So here the expected sum is to be 0 and C out to be 0. So this will be like 8 times but with different values, and this hashtag 10 is nothing but the time delay that we used to give in VHDL also. In after every condition we used to put some 100 nanoseconds delay or some. So this is the code. Let's try checking it. Check syntax. The syntax was successful. Now you can see the behavioral model over here. So this we can see here the A, B and C is 1, 1, 1 and the sum and carry is also 1. So now let's head over to our truth table. Yes, we can see over here that input and outputs are matching, so our code was correct. Over here we can see. So that was about Verilog. So conclusion and key takeaway is simple that Verilog is a very powerful tool. It is flexible and powerful language for designing digital hardware, and also understanding how we understood how to implement a full adder in Verilog. Also, Verilog design flow, the process of writing, simulating, and testing Verilog code is crucial for creating reliable, efficient, and digital circuits. Thank you so much.